Kia ora koutou katoa, ko Mike Plank tako ingoa, he ahorangi ahau I te whare wānanga o Waikaha. Kia ora Dave, thanks very much for the introduction, and yeah, it's a great privilege to be standing here today. Very exciting to be here and to be admitted as a new fellow. So I just want to talk today a little bit about my research area and the sort of research journey, I guess, that I've been on. So my research area is in mathematical modelling. I'm a mathematician by training, and a question I sometimes get asked is what is a model? And so I guess today I'm just going to sort of step you through with a few examples and talk about some of what modelling is and some of the value that it can provide. So here's my kind of one sentence on what a mathematical model is. So a simplified representation of reality that's expressed using something to do with maths. So mathematical rules for how different variables or different agents behave and interact. And one sort of important thing to understand about models is that they exist on a spectrum. So there's a whole spectrum from very simple models through to very complicated models. And here's my sort of metaphor for that. So if we wanted to have a map of London, we've got on one side here this sort of very stylized, simplified representation, the famous London tube map. And then at the other end of the spectrum, maybe some sort of complicated 3D visualization with a lot of detail about the city there. And so different models have advantages and uses in different situations. You know, if you want a simple way of knowing how to get from A to B, this simplified model here may be very useful. And so more generally, you know, if you want to make detailed predictions, if you want to understand heterogeneity, things like that, maybe you need quite a complicated model. But in other situations, if you're really just more interested in the main drivers of a particular system or what's sort of the main cause of a particular observation, then perhaps a simpler model is good enough. And so there's this famous quote or paraphrase that's sort of most commonly attributed to Einstein, which is that things should be made, or models should be made as simple as possible, but no simpler. And so what I think this quote is getting at is that simple models can be good, and actually if you make a model too complicated, if you try and put too much reality into a model, you can lose some of the value of having a simplified representation. You start to lose, you start to have the sort of minor details obscuring the main drivers, potentially. So in my research career, I've worked on applying mathematical models in a wide range of different areas, mostly in mathematical biology. So my PhD was actually on modeling cell behavior in cancer, so some of the pathological types of cell behavior that occur during cancer progression. I did a postdoc on modeling cardiovascular disease, modeling plaque formation, and again, some of those sort of cell-based models. And then since then, I've worked on marine and freshwater ecosystems, pest populations and control, fisheries management, infectious diseases, language revitalization, child welfare. So quite a wide range of things there, and quite a wide range of scales. So the scales there going from the microscopic scale through to these sort of big society-wide kind of all-encompassing things like infectious diseases or languages. And that's involved a huge amount of interdisciplinary collaboration. And so almost all of the modeling work that I've done has been in collaboration with domain experts, from microbiologists and ecologists through to epidemiologists, public health experts, and policymakers. And so you might be thinking, well, what, you know, this is just a sort of scattergun of topics. What's the sort of connection? And so I would say, you know, the connecting theme that's kind of run through the research that I've done is that I'm aiming to use the language and the tools of mathematics and statistics to try and understand how some of these complex systems work, to sort of try and strip away some of the detail, really focus in on the core mechanisms and understand what those core mechanisms are and how they work. Predicting how complex systems might respond to change, Testing different hypotheses. So often, a researcher in a particular area might say, well, we've got these observations, we've got these different hypotheses about what could be, causing what we're seeing. And sometimes we can use models to kind of probe those questions and test which of those hypotheses are actually consistent with observed data. And finally, to inform management decisions and interventions. It's very difficult in many situations to run an experiment. You can't run an experiment where you introduce some policy into society. So sometimes having a model and trying to get a handle on what the effects of those different policies might be, it can be really useful. So that was me up until about 2019, and then we had this thing called a pandemic, and all of a sudden mathematical modeling and the work that myself and my team were doing were kind of thrust into the spotlight like nothing we'd ever seen before. So this was obviously a really intense part of my career and period of work. I think, I look back at my records, I think we had something like 200 meetings with government policymakers and officials, and we produced about 60 written reports to government over roughly about a 2.5 or 3 year period. And so I guess I just want to sort of finish off by sort of describing what I see as the value of that. What was the value of modeling during the COVID-19 pandemic? Obviously our results and the work we were doing were being used to help inform some pretty momentous decisions. And so what was the contribution? And I think a lot of people, when they think modeling, particularly in this sort of situation, they think modeling is about predicting. So predicting the future, what's going to happen next. And that can be part of it, but it's not the only part. Actually, I think there's quite a broad range of different contributions that modeling can make and did make. So firstly, situational awareness, really just understanding the situation you're in, maybe the direction it's heading, the potential impact that situation could have if things are left unchecked. Making sense of data, you'll often see, particularly in the media, you'll often see things like models say this or data says that, but it's almost always actually a combination of the two, right? So raw data on its own tends to be pretty messy, it's biased, there are things missing. So if you just look at raw data and you don't really have any sort of quantitative tools around that, it can be quite difficult to make sense of that data. So often you need some models, you need to maybe make some assumptions about the processes that generated that data in order to be able to extract some useful information and some insight from that data. Okay, and likewise models are very rarely just models on their own. They're not just things that are made up. Usually there's a lot of data that's underlying those models and being used as an input. So models and data again sort of exist on a spectrum, and there's a range there. Challenging implicit assumptions. I think whenever any of us have to make a decision, we've normally got some mental model going on about what the consequences might be, what's going to happen if I make this decision versus that one. And I think that happened, during a pandemic response as well. So people who are involved in the response, involved in making policy, involved in making decisions, have these mental models that they're using to try and think about what's going to happen next. One of the values I think exists in modeling is that it actually forces you to be really clear about what those assumptions are. So we're really strict about writing down our assumptions. You've got to write them all down. And actually, when you do that, that's when you realize, actually, that's a really stupid assumption. or you understand the consequences of those assumptions a bit more, and you maybe think about, actually, if I made this different assumption, things could look a little bit different. And so that helps build understanding. Other areas where I think we kind of provided value, so evaluating intervention effectiveness. How effective was this particular control measure or this intervention that was introduced in response to the pandemic? Comparing different policy options, as I alluded to earlier, you've got a choice between instigating this policy or that one, or various options, various sort of variations on what those policies could look like. And modeling can help you sort of get a gauge on the relative different outcomes between those policies. It might not be able to say, if you do this policy, there'll be 463 cases, and if you do this one, it's not at that level of detail, but it can help you kind of gauge the relative differences between them. And then finally, I think, through some of the communication work that myself and my team did, I think an important role was kind of helping the public understand the rationale for some of the decisions that were being made and the strategy behind the pandemic response in New Zealand. And so my final kind of one sentence summary or one sentence pitch, I guess, for the value of models. Models are not a crystal ball. They can't predict the future. They certainly can't tell you what to do. Okay, but I think they can help you make decisions with a fuller understanding of their likely consequences. And so that would be my, my sort of summary of what modelling added to the pandemic response. So it remains for me to really just say thank you. So huge thank you to my family and to the huge number of students, colleagues, co-authors and mentors that I've been immensely lucky to work with over the years. I couldn't have done any of it without them. Far too many names to list on a slide or to sort of say. But yeah, huge thank you to everyone who's been involved, and thank you to you all for listening.
Awesome. Early in my career, I did work with mathematical modelers, and I always thought, other than the fact that at the time I thought they were bastards, because what it did is peels back your assumptions, and when you sit there with somebody that's thinking in terms of structures, you can trip over your own feet really fast. So I always think of modeling as sort of clarity of thinking in terms of stripping out, the essential bits and what are the add-ons and that. And I've always been fascinated. I'm absolutely terrible at it myself. But as with many things, when you're an ecologist, you know a lot about a few things, so you're dangerous in many subjects. But I've always appreciated the sort of work that really good modelers can do. And it also reminds me, something like Neil as well, the world changes and suddenly you're the star of the show and you think, wow, how did that happen? And so what a marvelous thing to happen in your career. So awesome. Who's got a question? I'm sure you all have questions of a simple nature that you want a complex answer for.
I've got a simple question, which will probably have a very simple answer. I was just interested in what led you down the biology path as opposed to any other sector where modelling could be applied.
Yeah, good question. It wasn't a conscious decision. It was. I mean, my PhD was in that area, and what I could see was that it was quite a big growth area in mathematical modelling at the time, and that's continued to be the case. So I think, models have been used obviously in physics and physical systems. Biology is just so much more complicated, and so I think that's really why we've seen that sort of big expansion in that area. And I guess I've just piggybacked on that really. But I mean, I always, had a fascination with biology, from the start, from the beginning of my research career, and just gone with that. Yeah.
Yeah. Kia ora. Michael, thank you for a really interesting talk. My question is, you've clearly done a lot of collaborative work across your career and working with people from quite different disciplinary backgrounds. And I wondered if you had any reflections on what you'd gained from having worked collaboratively across so many different disciplines.
Not other than just it's a lot of fun, really. And you just get to meet lots of different people, and you collaborate with the people who are fun. So my approach to new collaborations has always been, if this is a fun person, they've got an interesting research question, or they've got an interesting topic, then let's think about something where we might be able to work together, and just take it from there, really.
Yeah, I was just interested in whether it's part of normal procedure. Think about the pandemic or some of these other crises where there tends to be a witch hunt some years later. It's going on at the moment. So is the modelling involved in that to look at you got some chance of looking at the counterfactuals and things like that in the modelling, or is the modelling just all set aside and it's now just in policy space?
No, absolutely. I mean, we can certainly look at counterfactuals in modelling, and there's been quite a lot of effort, obviously not just from me, but internationally, in looking at different counterfactuals, and some of the work that we've done as well has looked at, what things could have looked like under different policies. Yeah, absolutely. So that's part of it. Yeah.
So involved in
Not directly, but I think it's, I mean, certainly some of the evidence that we've produced from that type of work has been looked at by, for instance, the Royal Commission. And so it has fed into that, maybe in a relatively minor way, but it is there, yeah.